Okay, okay, okay. What is that? Okay. So, okay, it's working. It's no, no, I don't need it. Just with this laser or not? Yeah, this. But don't worry, don't worry. Okay, okay, perfect. Don't worry, don't worry. Never mind. Okay. Take some water here.
Right. So before we start with Eric's talk, actually, I forgot to say something earlier on. I didn't organize this thing on my own. The two of the co-directors are here, Jenny and Bruno. Please, just so people know who you are. If you have a problem, you can also ask them for help. But yes, okay. So with that, please, Eric, go ahead.
Okay, thank you very much for the invitation. It's also my first time in Natal, and also not my first time in Brazil. I love Brazil, so keep inviting me, so it's always a pleasure. So I will try to talk a little bit about this kind of hot topic right now, that is twisted bilayer graphene and all that, and made it anchor and that. So I wanted to do a sort of a story of how it all evolved and how this have become into what it is right now. So I coming from university in Valparaiso. It's not so far, but anyway, it's like 6 hour flying. So we are in the same continent, but it's still a little bit far. So and we are in the middle between Viña del Mar and Valparaiso. There's also a nice museum there, a house of Pablo Neruda, one of the Nobel Prize winner writer. So it's a very nice place to go once you are there. And we have these lovely views. Not that the water is not as warm as here, so don't go there. So, but it's really nice, the view. And this is our university. Is around 80 years. It was founded by somebody who made money with sugarcane or something like that. Okay, so first, what is a moire pattern? If you take two periodic structures and somehow you rotate them, so you will obtain this superstructure, and you can do basically with almost any form, with any shape. If in this case it's like 3-4 layers of this square lattice, or it has been used in fabrics in the textile industry for a long time, so to obtain this kind of, I mean, for that time they were like very, very modern, but right now it's like not very useful. But anyway, in physics, in around 1990, when they started looking at STM images, When you put it in the highly oriented pyrolytic graphite, that is HOPG crystal, one of the first things they observed was this kind of a huge superstructure. Because, as you know, the graphene lattice constants is around 2.46 angstrom, and they were observing this structure like superstructure like 5 to 10 or more nanometers between the distance, the lattice structure of this superstructure. So that was like a kind of puzzler for a while, because they were trying to understand what is the origin of that. And there was, of course, a lot of speculation and a lot of work at that time, because it was not very easy to understand how these moire patterns are coming from. So, but it was like I think it remained like a sort of a mystery for almost like 10 years, more or less. Not a mystery, but there was a lot of speculation on what is the origin of that. So, but it was already settled. It was known that it was coming from a region of the unit cell. But anyway, in 2009, we were playing with some STM machine we have at the university, and we have this HOPG crystal, and it was inside the chamber, at room temperature and a kind of very low pressure. And then we were measuring like for 2 weeks this crystal, and nothing happened. And then I decided one day to take out of the chamber and do this process of with the Scotch tape, remove the upper layers, and then we put it back in the chamber. And within 5 minutes, we were getting these images. It was like, wow. So, and from that time, we were trying to understand a little bit. So I read it and saw what was the origin of that. So, but at that time, there was not a lot of things done on twisted bilayers. So it was known that graphene has a direct con. The bilayer AB graphene have this massive band. So the question was, so what happens when we have this kind of a structure? So we decided to dig a little bit about it. So, and at that time, well, right now, if you look for twisted bilayer graphene, you get more than 12,000 hits. But in 2007, you will only get one article by Lopez dos Santos and Castro Neto, and that was the only article that at that time on twisted bilayer graphene. And they did it. I will speak a little bit right now. I will divide this in 2 parts, but they did a very clever model, because they treated the twisted bilayer like 2 rotated cones, or two rotated beryllium zones, and they were only concentrated around one of the K points. So the continuum model is only coupling the same K point, but in different layers. So a basic model will include a sort of a graphene-like terms for each layer, and also an interlayer coupling term. And that will give you the 2 parts. And the other, if you go into the reciprocal space, what they did is like a Fourier transform of all these hoppings. It was not so clear in the article because this was a letter, but what you can do is, like in the real space, get a map of all these interaction of all these hoppings between layers, and then go to the reciprocal space, and you end up with only a few terms that matters. So the model was like very simple, but it was working. So this is also a little bit about it. So it's also including some article I will talk about a little bit more later. Some works made by Bistrichter and McDonald. And the Hamiltonian is basically you are coupling one cone from one layer to the other one. So, but in the beryllium zone, you have like 3 of these cones, and the Hamiltonian you get is something like that. This is of course a little much more smaller than the one you get with tight banding. And there was this result that was very important at that time, so that the velocity of the fermions is renormalized. So Castroneto got this formula. This is well, the one, right now is like right now it's doing what was supposed to. Okay. So I go forward. Okay, so yeah, this is because it was very, okay. Okay, so you have one K point from one layer coupled to the others, to the other K point from the other layers. There's 3 because there are 3 direct counts in the beryllium zone. So and then you get this velocity renormalization, and it was not a clear picture of that, but you can expect that it goes to 0 at some number here. So this is, and also Lopez dos Santos, they were telling that the direct count, when you apply an electric field, it doesn't open a gap, so it just a band chief of the direct counts. So we decided to try to do another approach. So it was and try to do a tight banding model, and maybe and also a DFT calculation of that. So I will explain a little bit more what you are doing. I see that there are some students here, so I will try to explain with some details that if you start with a bilayer graphene, so you rotate one of the layers, but you need to obtain a commensurate unit cell. So you have to rotate in some way that you obtain also a periodic structure. So you choose a vector with M and N integers, coprime integers, and you rotate one layer from this point to this other one, and it's also a lattice point of the. It's also a lattice point. So and that gives you one of the vectors, and the other one you obtain just by 60 degrees vector from the original, and that way you obtain like the smallest. In that case, using N equals 1 and M equals 1, 2 and 1, you obtain the smallest unit cell possible is 28 atoms. And also, if you do some basic geometry, you obtain how many atoms in terms of N and M you will have in the unit cell, and also the angles you obtain. Of course, these angles are discrete. It's not, but you can play a little bit with all these N and M and obtain a quite dense spectrum of angles. When you build the unit cell this way, you will see that there's a region here that when one atom lies on top of the other, of course there's no other. When you build the cell that way, there's only one atom on top of the other, and you will see also another region where it's almost like AB stacking. At the origin, it's like the opposite is BA stacking. So you have like it's like 3 regions on the unit cell that later we see that they are like important. Okay, so the tight banding model is like not very complicated. I will add here this on-site term that is not needed in general, but this. And our first model was not so fancy as this one. We were using just a graphene model for graphene Hamiltonian for the layer, and just a distance-dependent hopping, an exponential decrease distance-dependent layers. So so it was very simple, only 3 parameters. But you can do it a little bit more fancy and do it like a Slater-Koster two-center approximation and do something like that. When you and here also there's not so many parameters. You have is A0 is the distance between the graphene atoms within the layer, and D0 is the distance between layers, and so you have like 2 parameters here plus the hoppings within the layer and between layers. So this is like the gamma 0, and this is gamma 1 in bilayer graphene. So with that, you can calculate the band structure. And what we found at the beginning was that for large angles, the band structure is similar to graphene, at least for low energies. So you will see here that is for, let's take this one, 21.8. This is for 2 and 1, the integers I told you before. And in green, you see these are DFT calculations, and the red dots are what a graphene layer would look like if in case the same size. And as you get, if the angles gets lower, you will see that the bands are getting a little bit flatter, or the dispersion is not like graphene, is renormalized. But once you get to around 1 point and something degree, you observe this kind of flat bands here. So it's like in red again is graphene, and in green would be like a bilayer graphene. So at that time we were thinking that this is kind of a transition angle, that if you go, okay, we were starting with AB stacking, so if you rotate, something happens, but when you go down or you reach 0 again, you obtain bilayer AB graphene. So what we were expecting here is that somehow below this angle, that later was called a magic angle, we will recover again the bilayer structure, bilayer AB structure. But it's not the case, because what happens is like a lot of oscillations. But I will tell you a little bit more about later. But if you do the simple calculation of how the slope changes with the angle, you obtain that. And if you plot like what is the difference in energy at that time we put it at gamma point, so you will see that it goes down. This is a minimum here around 1.5, and then goes up, and if you are looking right now, you see that it's going down again. But we didn't realize that at that time, so we are not so important, but it turned out to be very important. So also, if you calculate the density of states of the structure, you will see that depending on the angle, you will get these Hove singularities that they are shifting towards 0, to the Fermi level, as the angle gets lower. And this is a signature of that. When you have one of the first explanation of what is the origin of that, or why the twisted bilayer has this direct cone structure without any perturbation, is like, people were tending to think that there's no coupling between layers, so they behave like 2 separate graphene layers, so at large angles, there's no coupling between them. So we calculated that. This is This is the expected value, more or less, of the interlayer coupling. And you will see that as the angle gets lower, the coupling between layers gets larger, in energy. And but for large angles, it's also no zero. It's always a little bit of coupling, but it's not completely decoupled, as people were saying. But of course, if you get to a lower angles, the coupling gets higher. So more or less at that time, there came out a paper by Evan Drey and his group, and they were observing these Van Hove singularities in twisted structure, and they were, okay, one thing that is kind of important is that if you look at the density of states, or we calculated the local density of states, here the local density of states at AA point is larger than at the AB point. This is the points I was mentioning in the superlattice structure. So that tells you that all the electrons are going to this, or mostly all the electrons tend to go to this region AA. If you do the same calculation for a lower angle, this difference is getting larger. So it's like, this is for an angle actually very large. For a very low angle, this difference is huge. So as I was telling you, Evan Drey measured these Van Hove singularities in twisted bilayers. They did this path, and depending on where they were measuring the local density of a state, this differential conductivity, they were seeing that at the one, at this in the AA region, of course the intensity is larger, and they see like this split of these Van Hove singularities are in this region. Of course, later there was some article by some people like Tremblay, the Lesaudier, and they were trying to see what happens when the angle is actually very, very small. And this is a calculation for an angle around 0.2 degrees. The unit cell of that will contain like 800,000 atoms. It's kind of a huge calculation. So anyway, you see like these oscillations in the density of states. But if you observe how the local density of states is at the AB region in a atom or a B atom, it looks like it looks the same as in AB graphene. In the different atoms, it's a different coordination. Okay, Nuno were saying that in HOPE you see only one of the two atoms in the unit cell. That's because the density of states, or the local density of states of one of them is higher, so you will see only one of them. That's where. So the whole system is going toward the AB, but this happening through these kind of rapid oscillations, and this is kind of not completely understood what happened, but it's like that. So we will now we'll talk a little bit more about this continuum model, because there are some parameters we will use. And if you, okay, this is the reduced Brillouin sound, or the Moire Brillouin sound. This is the distance between the two K points, and you will see that it depends on the angle, so this theta. And if you couple the two layers, this parameter omega, or W, is like 1/3 of the coupling between the AB layers, and it gives you a measure of how the two layers are interacting. So if you, this is a sort of the gamma 1 gives you the separation around this endpoint, and as the angle gets lower, this gets larger. Okay, no. Well, no, it's the same value, but in comparison with the kinetic term is of the same, more or less of the same range. So as you see here, if you have a large angle, or if they are decoupled, you will see these two direct counts. But as soon as you couple something at this kinetic energy is much more larger than this coupling, you will see this kind of band structure. But when they are of the same order, you will obtain this, like the flank bands we were mentioning. This is the case when the interlayer coupling is more or less the same as the kinetic energy. And this is alpha, is a dimensional parameter that takes account of this, how is the relation between this coupling between layers and the kinetic energy. So this is McDonald. They also calculated the band structure of this structure, and here you will see the same flat bands, and also for the lower angles you will see some dispersion. Is not completely flat, and they proposed or they obtained another formula for the velocity renormalization, and this is in terms of this alpha I mentioned before. The alpha is around 110 millielectron volts. And when you calculate this with the continuum model in terms of alpha, you will get not only one magic angle, you will obtain also a set of these magic angles, different rotation angles. So we'll obtain something like that. Okay, so for a long time, there were always many people saying that it was just like a hobby, because it was very difficult to create this kind of superstructure, or this kind of a moire pattern. It's like random, because the beginning was like that. So people were starting trying to fabricate this twisted structure. One method was to using the tip of the STM to fold one layer on top of the other and create this artificial twisted bilayer. So, but this, of course, this is kind of complicated, and but a lot of people did that. So right now it's more I mean, like 10 years later or something, there's a whole process, and they are doing that a little bit more systematic. And if you do, you can do that using, this is this green is a PMMA resin, and if you put a HBN, so they attach an HBN layer on this resin, and they push it on graphene, and they are able to break this one graphene layer into two, and then lift one part and put on top of the other. And they can create this, or in this case, they created a bilayer structure. This is the region 2, and this is the Raman Spectra. But anyway, but they can also rotate the handle and put it on top of the other at the desired angle. So it is, right now it's not, well, it's not easy, but there are a lot of people doing that. So. Okay, with this, there were also a lot of articles trying to understand some of the properties of twisted bilayer. One of them is the optical properties. We have seen that these Hove singularities are reaching zero. But, and also, if you try, well, you can see, or you can study the optical transition on this material and see, well, at the end point, the transition is forbidden, but you can see also two clear transition here. In the, this is the continuum model, and you will see that this I region is at the end point of this, and so okay, let me show you first, and then so you will see that in this is how the optical absorption spectra changes with the angle. So you will see that this the absorption, or this maximum in the absorption, also changes with the angles. It goes lower in energy from the largest angles around here, so it goes all the way out to the milli-electron volts range. So it's, and this peak is associated with this transition at the end point of the brilliant zone, and there's also two other transitions, one at this the second region here, and the third one here. The second is Hove Singularities here. So this is how the spectra of twisted bilayer graphenes, and this is how it changes with the angle. Well, there are also, this is some other peaks here associated with this, because sometimes you will not attain a commensurate unit cell is not the same as the brilliant or the moire unit cell, because sometimes you don't get a commensurate unit cell, so sometimes you have a larger unit cell than the moire pattern. So, and these small peaks here are associated with that. It's just a small comment. And of course, the people were trying to find methods or ways to detect the angle of this structure, and they started to study using Raman, and here in Brazil they have a large community of Raman people, so it's a very strong community. So Jorio, Cansado, Pimenta, and all, they were studying this structure, and they using the first technique I show you, they observed that there's another additional Raman peak obtained in the spectra. This is around the D peak of the graphene D peak, around that region. But there were also another ones at lower frequencies, and here they were able to simulate and obtain how these modes are related with the dispersion, the form dispersion. And of course, they had to take into account that the wave vector of the moire brilliant zone is important, and if you don't take that into account, you wouldn't get the proper result. So the peak is defined by frequency, and also the Q is also a wave vector defined by the angle. Okay, so it is also possible, we explore how this, in 3 layers, how the twisting of one of the layers affects the band dispersion, and you will get something similar to, for large angles, something similar to ABA graphene, but there's a band gap here, and also a direct con. So there's okay, Rodrigo, we will talk about it later because I haven't shown you that, but it's also a band gap here in 3-layer AB. And the origin of that, we are currently, is related with charge transfer from one layer to another. And also, if you calculate for lower angles, you will see that this is the bands, the parabolic bands are here, and the cone is like going down or flattening, and you will observe this kind of structure. So it's also a flat band plus this parabolic dispersion, but all of the structure are flat. This is not very explored yet, so maybe it's open for more research. So. And also you get this velocity renormalization of the direct cone, and you will see this also, and you will get also this oscillation in the velocity around below this magic angle. Okay, so go back to our figures. So we were like a puzzler of why this. If you notice that here, there's these very bright spots at the end, and if you do a zoom around this region, you will see that these bright spots are not going or they are not, they don't have the same periodicity of the bulk moire pattern. And we were like kind of puzzled by that. So it's what happening here? So as you see, this is the bulk, and this is the moire pattern, the bright spots at the end. So this is supposed to be at the end of one of the layers, and there's another layer below. So we were trying to understand that. So if we did some simulations of what is happening, and if you see here, the moire is around here. This is a ribbon on top of a graphene layer. So if you see here, this should be the moire. Here is the AA region, but you see that for lower energy, the local density of states is larger at this region. If you calculate for larger energy, it's like the same like the tip of the STM with higher voltage. So you will get the density of states, or the local density of states at another region. So you will get the moire pattern and also the localization in another region. So what is happening? So the explanation is very simple, and it's because the edge set the rules. If you have a AB ribbon, you will get this kind of edge states or close to zero energy. But if you have if you do a stacked AA ribbon, you will get this. The energies are shifted away from the Fermi energy. So at lower energy, the simple explanation is that the electrons prefer to go to the AB regions in the edges because the AA are at higher energy. So it's a very simple explanation, but we were like kind of puzzled for a while. And of course, this is just for completeness. You see that the density of states, how it changes with the size of the ribbon. Of course, if you a very wide ribbon, you will reach eventually the bulk, and this also the H states. Okay, so just something very fast. If you put graphene on top of hexagonal boron nitride, so the two of them they don't have the same lattice constant, so you will get also a moire pattern. At the beginning, there were some suggestions that you will get a gap because of the lattice asymmetry, because we have one boron on top of carbon and another nitrogen. But this is not the case. Actually, the origin of the gap is still in debate, but it's because of this a long range periodic potential. But anyway, if you put graphene on top of boron nitride, because this is an excellent isolator, and you will get this like the corrugation is like way later. So this is in silicon oxide, and if you compare with over hexagonal boron nitride, so you will get a higher conductivity and all that. So it's an excellent substrate. But in this case, they were obtaining the direct con. But as I mentioned, if you have this, as a consequence of this superlattice periodic potential, you will get, and this is based on this one-dimensional calculation, you will get also these direct points away from the Fermi level, and they were also observed experimentally by this group. And here, as you can see, maybe with good eyes, they would say that this is it's not completely semi-metal here. This is a small band gap. Okay, but later, so there were people trying to create like a new area. This is like, they were calling these twistronics, and of course, I hope it would be that easy, but they tried to, these people, they created like sort of a machine to rotate and study layers. This is hexagonal boron nitride, and using the tip of the STM, they were able to move like this structure here to push around here and rotate this. So it was kind of neat, so it's very interesting. And of course, they were able to study how the friction depends on the angle and all that, so it's kind of very interesting. And if you see here, they observe a gap at the charge neutrality point. And that's where I was telling that this is still a matter of debate. But anyway, it happens when the graphene and hexagonal-boron nitride layers are perfectly aligned. So if you want to obtain a very good graphene, you should avoid to have the hexagonal-boron nitride and graphene layers. They shouldn't be aligned. So the angle between them should be no zero. So because it creates a gap here. Okay, so let's talk a little bit more, a little bit about this finding that sort of revolutionized the area, because in 2018, Jarillo Herrera and his group found that this the one electron picture we saw, this is not a band gap here, so it's completely metal or semi-metal. But in this, when they were measuring that, first, you have like these three scenarios. When you have an insulator, it's perfectly, you have a metal here, but suddenly a system that should be a metal suddenly becomes an insulator. That's because there's a correlation between electrons there that creates a band. And this a well-known model by Hubbard, when you put you have electrons and you put a Coulomb term, and you can open the gap using this. And what they got is, what they were thinking is that, well, they have this structure. This is hexagonal-boron nitride, and then they have a gate here, so they can play filling of the bands, and they have this twisted bilayer graphene, and they were trying to get precisely this magic angle. So this is what they are expecting, the band structure. This is the flat bands, and what we were telling you, that the localization in the reciprocal space is the same. The flat bands in the reciprocal space means localization in the real space, and you will see that you get that these AA regions, you will get this high density of states. So it's like having a set of triangular lattice of these AA regions with a lot of electrons there, so they are coupled. And let's see what happens. So they did that. So if you get an angle for around 3 degrees, the conductivity is like that. It's like graphene. But if you get around 1.8 degrees, still not a magic angle. They see these insulating gaps here at complete filling. This is the electron on the whole side. But this is because the bands are separated from the rest, so it's not quite unusual. So this is expected, more or less, and still they have here the conductivity like graphene. But if you move to the magic angle, you will get also these insulating states at half filling here, around this region. You will get that. And also, this kind of, I think there is no explanation for that. If you put an external magnetic field, you will get also, this is the conductivity. This is already insulating state. But if you put a magnetic field, you will get also a metallic state. So the idea is, okay, well, what is happening? Because you have an insulated state, if you put a magnetic field, you will get Landau levels, so you get more insulating states. So anyway, they got like this region with the conductivity is, okay, it's becoming like a metal. But Jarillo is proposing, or they are thinking that this is something like a Zeeman effect, like if you have like two spins and one is going up and the other is going down. So there's also a region where they can they became a metal. It's like the Zeeman effect with two spins. But again, I think this is there's more room here for research. And also, they were investigating at the same time what happens at this insulating state here, and they were measuring the conductivity. This is a I think I remember this is a two-terminal device, and here they are not in this region. They are not reaching yet the -2, and they were obtaining a peak here in the conductivity, and they were like kind of puzzled of what was happening, and they decided to do another experiment with a 4-terminal device, and they obtained it for, this is for 1.05 degrees. They obtained this. Okay, this is a zero resistivity. They mean around 1 Kelvin. They did also another test and all that. So you can watch this presentation by Harillo on the internet. And later this year, there was this group. I don't remember. Okay, no. They were studying the same material. I mean, twisted bilayer graphene. And this is for a magic angle. They observed, I mean, the peak in the resistivity, the insulating state, but they were like they have this mechanism of exerting pressure to the sample. And remember that I told you that these dimensional parameters that covers the layers are related with the coupling between layers and the angles are actually related so if you increase the coupling between layers, you will get the flat bands or the magic angle at the higher angle. So they were like, okay, let's do that with 1.27 degrees for this angle. If you don't apply any pressure, you won't obtain any insulating state or superconductivity. But they applied the pressure and they obtained these insulating states here. Even they obtained some state that Harillo didn't find in the pristine 1.1 degree. So this is at half filling here, so there was not observed anything. So it was like kind of a confirmation that the continuum theory or the theory works, that it's the same pressing the layers and the copper, when you press the layers, when you apply pressure, the coupling between layers gets larger and the magic angle goes up. Okay, this is, remember that this is the brilliant zone is very small, and this, I've read that this is the superconducting temperature is related with the size of the brilliant zone, of the size of these flat bands. So if you get, eventually, if you get these flat bands at a higher angle, so you will get a larger moire zone, and eventually the superconducting temperature will go up. But this is something theoretical, and let's see how it goes. So anyway, there was also another finding here that they found ferromagnetism at this magic twist angle. This is kind of, I think nobody understands what's happening right now, but they were like doing these measurements of the whole slope, and suddenly for some filling, okay, the filling is that you are changing the gauge, so you can reach different fillings. So at a certain filling, that's 3/4 filling more or less, they obtain this like weird behavior here of this slope. And if they measure the whole resistance, they see like this hysteretic behavior here. It's like, looks like something ferromagnetic. So they did this test, and this the whole resistance goes up, is higher around this 3/4 filling. It also depends on temperature, so it's related with these states, and all these states, when you increase the temperature, it goes down. And they are pushing, and I think it's not completely settled. For an explanation for that is it's like if you have remember that in graphene you have like four states, one per valley, one per valley plus one per spin, and if you are somehow split this, you will get all these insulating state, and the shear number associated with one of these electrons change from -1, 1. If you integrate the 0, but if you are able to get between these, you will get a non-zero shear number, and eventually you get orbital magnetization of that. The problem with that approach is that they are not getting any constant, the quantization of the resistivity is not like an integer number of the, so it's not completely settled that issue. Okay, this is also, that was also another idea that is coming for a while, because remember that I told you that here in the center we have the AA region, and around is surrounded by AB or BA stacking. And there was a long time paper, if you have a AB stacking bilayer, if you apply a bias, you get a gap. But if you somehow are able to change the bias and create two regions with different shear numbers, you will get like this topological edge stays in the middle. So, or the same happens when you open a gap in AB region and BA region. So the both regions will have different shear numbers. Eventually, you will get between this region these topological currents around here. Of course, this is not so simple. You have to, the size of these regions should be large enough for so the states are not rapidly decaying to one another, so there are not interaction between them. So I guess this is also around 0.2 degrees, or this is a very low angle. So you will get this. This is a theoretical article by Pablo and others. So, and also it was like measured last year, and this is like the same, but this is the states. This is the AA region. This is this stays at the edges of the AB regions. Okay, just also this is something it was found that in this structure, if you rotate the layers, they are chiral. So it's not the same looking at this rotated structure from one side and the other. So they did this measurement, and they were able to rotate the layers in one direction and on the other, and they see that the absorption of circular polarized left and right light depends on how the layers was rotated. This is well known in chemistry. This is a optical activity, dichroism. So they measured that, and they see this behavior that the two, this is left-handed and right-handed, how they change it when you do the mesh for different rotation angle in one direction and the other. So in one case, this is the what? Oops, I forgot the name of that. It's like the rotational angle is rotate is like. Oops. Okay. No. Anyway, is a measure of how the axis of polarization is changing with the with the energy. So it's in this case, you will see that for one, if you rotate in one direction, it's different to the other. So it means that it's absorbing more one kind of circular polarized light, or left or right. So we created like a sort of a model of that. I won't go into much details about that, but the main point is that you can't use the Kubo formula just like that. So you have to take into account that the light going from one layer to the other is changing their phase a little bit. So you have to take that into account. So you have to the conductivity will have this shift. We have this exponential factor depending on the how the distance between layers. So if you do that, okay, that's what was mentioned, that this is the chiral symmetry. So if you do that, so you are able to obtain these nice figures. This is the ellipticity. Oh, I forgot. This is the ellipticity. Was the image. Okay, so and these absorption peaks are more or less the same I was showing you before in the Cochino's article, and they are related with these peaks around here. But at the end, the explanation is that it's important that when light interacts with one layer and goes to the other, there's a small rotation between the direct cones. And this rotation is what makes the absorption different in one layer and the other. So if you, in the continuum mode, you take out this rotation of the spinors, so you won't get the effect. So it's kind of a tricky, but you will get this ellipticity or the difference in optical absorption in twisted bilayer. And just want to mention, the effect is larger, the larger the angles. For low angles, the effect is almost nothing. Okay, just a little bit. So okay, this is another structure. We were like playing with that. So this is a semiconductor. If you rotate this layer, this is blue phosphorene, this allotrope of phosphorene, but it has an external lattice like that. So you will get also these flat bands here. We haven't explored that in details, but also you get this kind of flat bands. Okay, and then I also want to thank also my collaborators and some people from our university, Patricio Vargas and Monica Pacheco, and this is our people from Madrid. We are collaborating from a long time, but this is some people also from Brazil and some other from Chile, and also from Colombia here. Okay, thank you very much.
In first time, I would like to say congratulations for your presentation. I like a lot. And